Hello. Want to give you a heads up on what we got coming up next. It is not the easiest thing in the world. If you think back, we've got proofs. Proofs were from geometry, but we also have them in Algebra 2 as well. Now, what you need to know about these proofs is that, unlike the proofs we did in geometry, where we had theorems and postulates that we could follow all the way down, there's not theorems or postulates here. It's just straight algebra skills. Now, there are some steps that we'll follow to get to there, and let's get started with that right now. So, we have a proof, mathematical induction. What is mathematical induction? It's a type of proof. Mathematical induction is a three-step process. The very first step is that you show that the statement is true for some integer n. Typically, I like to do n equals 1. Do the very first term. Show that it works for the very first beginning value. Step 2. Here comes the fun part. We never got to do this in geometry. Let's assume that the statement is true for some positive integer k, as long as k is greater than n, which is what we had to begin with. K, or our n before was like 1. So as long as we pick a value that's bigger than the one we started with, we're just going to let k be some positive integer. That's an assumption. And then comes step 3. Now we need to show that our statement is true for the next integer, k plus 1. It's a variable. So let's do a quick little problem here. Our problem that I want to do says prove that 8n, 8 to the nth power minus 1 is divisible by 7. So our first step, let's show that this statement is true for some integer n. So I'm going to let n equal 1. So that means a to the first power minus 1 would equal 7, which is divisible by 7. So when n is 1, this is a true statement. A to the nth power minus 1 is divisible by 7. It is true when n is 1. Now, step 2. I'm going to assume. So I'm going to assume that 8 to the k power minus 1 is divisible by 7 for some positive integer k. So, what does this mean? This means that there is some whole number r such that 8 to the k power minus 1 is 7 times r. Now, our step 3. I have to show that the statement is true for the next integer k plus 1. How do I do that? Well, I let n equal k plus 1. So I start with my problem. 8 to the kth power. I got something in there I don't want. There we go. A to the k power minus 1 equals 7r. I'm going to add 1 to both sides here. So when I do that, I get 8 to the k power equals 7r plus 1. Now I'm going to go ahead and multiply both sides of that equation by 8. As long as I do it to both sides, I'm okay. So I'm multiplying both sides of the equation by 8. Well, 8 times 8 to the k power, a rule is we just add those exponents. So I have 8 to the k plus 1 power equals, well, I'm going to distribute it on the other side. So 8 times the 7 plus 7nr, sorry, 8 times the quantity 7r plus 1 is going to be 8 times 7, which is 56, r plus 8 times 1, which is 8. Well, now I'm going to subtract 1 from both sides. That way it gets back into the right format that it had to be. So I get 8 to the k plus 1, 8 to the power of k plus 1, minus 1 equals 56r plus 7. Well, that's not the right format. I need to show that this is divisible by 7. So I'm going to factor out a 7 from both sides, or from the 56 and the 7. So now I have 8 to the k plus 1 power minus 1 equals 7 times parentheses 8r plus 1. Well, now here's something to note. We knew that k plus 1 was n, so now I have a to the n power minus 1 equals 7 times 8r plus 1. Since r is a whole number, then 8r plus 1 also has to be a whole number. Thus, 8 to the nth power minus 1 is divisible by 7. since 7 times a whole number is 8 to the nth power minus 1. That is one proof. Notice, like geometry, it takes paper. It takes space. Let's try a different problem. So let's prove that each statement is true for all positive integers. So the problem that I have here, problem number 11, is out of the textbook. It's 1 plus 5 plus 9 plus ... So it's going to go on forever. Plus 4n minus 4n minus 3, that's in parentheses, equals the quantity n parenthesis 2n minus 1 close the parenthesis. So they have some formula here that 1 plus 5 plus n plus ... all the way up to 4n minus 3. So if I add all those terms up, if I just know what the n is, I could have just took n times 2n minus 1 and got the exact same sum. So it's just another way to find sum. So I need to prove that this statement is true for all equations. So my step 1 is I'm going to let n equal 1. So when I do that, it tells me that 1 would have to equal 2 times 1 minus 1, which is 1 times the quantity 2 minus 1, which is 1 times 1, which is 1. So I get 1 equals 1. My step 1, when I put n equals 1 in there, I get a true statement. So their formula works when n is 1. Now, I'm going to assume for step 2 that k is a positive integer, and that 1 plus 5 plus 9 plus ... plus 4 times k minus 3 does equal k times 2k minus 1. I'm going to assume that's true for some integer k. Now, step 3, I'm going to let n equal k plus 1. So if I'm going to go k plus 1, I'm going to start where the statement that I just had, that 1 plus 5 plus 9 plus ... plus 4k minus 3 equals k times 2k minus 1. And I'm going to add the next term onto both sides. The next term is, I got it in brackets, so bracket, 4 parenthesis k plus 1 minus 3, close my bracket. I'm adding that value to both sides of my equation. So now I have 1 plus 5 plus 9 plus ... plus 4k minus 3 plus bracket 4 parenthesis k plus 1 minus 3, close the bracket, equals k times 2k minus 1 plus bracket 4 parenthesis k plus 1 close parenthesis minus 3 bracket. So all I've done is add the next term to both sides of this equation. Well, now that I've done that, I'm going to just work with the right-hand side of that equation. So the first thing I'm going to do is I'm going to distribute the k to the first parenthesis, and I'm going to eliminate the brackets and the parentheses out of the other one. So when I do that, I get a 2k squared minus k, that's the first part, plus 4k plus 4 minus 3. Okay, I got to clean that up some more. I got a minus k plus a 4k, that would be a 3k. I got a 4 minus a 3, that would be a 1. So I get 2k squared plus 3k plus 1. So my whole 1 plus 5 plus 9 plus ... plus 4k minus 3 plus bracket 4k plus 1 minus 3 close the bracket is equal to 2k squared plus 3k plus 1. Well, now what I'm going to do is I'm going to factor 2k squared plus 3k plus 1. Now, I have a little note here for you. To factor, you either have to remember how to do it from Algebra 1, or go back in your book and look at pages 239 242. That's the whole section on factoring in our book. That one section, 239 to 242. The whole thing on factoring. So you can look it up. So what I did is I took a look at 2k squared. Well, the only way I can get 2k squared is I got to take k and 2k and multiply them. So I put a k in one parenthesis, I put a 2k in the other one. Now, the only way I can get the plus 1 at the end is to multiply 1 and 1. And since the middle term, the 3k in the middle was positive, these both had to be positive. Now, if I FOIL out k plus 1 and 2k plus 1, I would get 2k squared plus a k plus a 2k plus a 1, which would give me the 3k in the middle. So that does work. Now, here's a little note here, side note to myself. 2k plus 2 minus 1 is the same as 2k plus 1. So I'm kind of substituting that in there. Because what that allows me to do then is to say that k plus 1 in parentheses times bracket 2 times k plus 1 minus 1 is equal to 1 plus 5 plus 9 plus ... plus parentheses 4k minus 3 plus bracket 4k plus 1 minus 3 bracket. So when I look at this, I have proved that just by adding the 4k minus, or the 4 parenthesis k plus 1 minus 3 in brackets, I could have just put a k plus 1 into the formula of the original problem. And if you think back to that original problem, it said n times 2n minus 1 is the sum of everything else. Well, our n in this case was k plus 1. I now have k plus 1 times 2 times k plus 1 minus 1 in parentheses. I have proved it. That's mathematical induction. That's what you're going to be doing tomorrow.